Okay, so we are going to go through class 4, continuing where we left off. This is algebraic properties of regular expressions. And so we are going to go through today's lecture, probably all in one shot here rather than taking a break. But let's go ahead and get started. Okay, so the first thing is, as a quick review, regular expressions had the following ways of being created. There were the primitive regular expressions, which had lambda, which is just the language of just the empty string. We have the empty language, or the empty regular expression, the null symbol, and that's a regular expression that defines a language with no strings in it. We have a symbol from the alphabet, which defines a language of just that, the string of just that one symbol from the alphabet, like that. And then those primitive ones, or the basis expressions, can then be operated upon by any of the operators we have here. So the union operator, or the vertical bar, the OR symbol, essentially is a regular expression that's the union of the two languages of each of the expressions. The concatenation operator, which would just run the two expressions together next to each other, that is the concatenation of the first one with the second one. So those two languages concatenated together. We have the clean closure, or the star operator, star closure, and that defines the language of that star, which, remember, star is 0 or more concatenation. In other words, we concatenate R, the language of R, with itself 0 or more times. So because of the 0, that includes lambda. And then plus is the same thing, but is 1 or more times, so it does not include lambda. And then the last one is just an expression in parentheses, does not change the language, but that's used for grouping. And then we had our order of operations. Things in parentheses go first, and then plus and star from left to right, and then concatenation, and then union. Okay, so that brings us to this concept of equivalence of two regular expressions. And essentially what that means is if we would call two regular expressions equivalent if they define the same language. In other words, remember, a language is just a set of strings. So if the set of strings defined by one expression matches the set of strings defined by another regular expression, then those two regular expressions would be called equivalent. They don't define something different. There's no different elements in one or the other one, so therefore they have to be the same set, so the expressions are equivalent. So an example would be this A star is equal to A plus. So notice that there's 1 followed by 0 or more. And since that's essentially 1 or more, then that's the same as A plus. And note that that can be abstracted, not just with that regular expression A, but if X is some regular expression defining a language X, then X concatenated with X star is always going to be X plus. So that will always hold true. And that example that we had up there, since that would always hold true no matter what we plug in for X, then that can be considered an algebraic property of regular expressions. In other words, just like with algebra, we have certain truths about how we can manipulate things to get something that's equivalent. We can do the same thing with regular expressions. All right, so algebraic properties are something that we're used to from arithmetic and algebra, meaning that in this example here, like 1 plus 2 is the same as 2 plus 1, that we know that's true in a couple ways. One is we could show that. We could say 1 plus 2 is equal to 2 plus 1. We could solve each one on each side and say, well, 3 is definitely equal to 3. But note that you can also then abstract that into a general algebraic law or an algebraic property. And in this case, any x plus y is always going to be equivalent to y plus x. In other words, those have the same meaning. You'll always get the same result no matter what you plug in for x or what you plug in for y. This is always going to be true. So that is a property, an algebraic property of arithmetic. In this case, that's what, I don't know, the second or third grade or whenever you learn about that, that's what you call the commutative property or commutative property. The things when you have something plus something, you can just switch which side they're on and it does not change the result. Okay, so algebraic properties of regular expressions, we have those as well, just like we have them for algebra and arithmetic. And the idea here is two expressions that have variables are equivalent if the two expressions always produce the same languages or same language regardless of what languages we substitute for the variables. In other words, that's essentially what an algebraic property is. It doesn't matter what we plug into some variable, we'll always get the same, an equivalent one by manipulating it in that particular way. So back to here, like this is an algebraic property of addition. The commutative property or commutative property of addition says you have two things separated by a plus sign, you can just switch the order of them and it will not change the value of it. All right, so the commutative property basically says we can switch the order of operands and get the same result. So if we have an operator and we have the operands on either side of it, the commutative property says that those can switch and it will not change the result. The associative property says if we have some operator appearing more than once between a list of things, like A plus B plus C, then, so here's the three things, here are the operators between it. It doesn't matter with these three things, I don't know if you can see that or not, it doesn't matter with these three things what order we put them in, that we can actually do these two first, or we could do these two first, it doesn't really matter. And let's take a look at those with regular expressions. All right, so commutative and associative properties. So in our case, no matter what language this is, no matter what language that expression is defining, that union with S is the same as S union with R. So that shows that the union operator is commutative, meaning that just like plus in algebra or arithmetic, we can switch the order of those without changing what language we get out of it. Also, union is associative. In other words, if I do R union S, and that gives me a result, and then I union that with T, that's the same as if I take R and union it with S union T. And notice with union that makes sense, because with union we're just saying, take all of these elements of this set and put them in with this other one. In other words, we're just putting them into a basket that has all of the elements from both of them combined. So in this case, we're dumping all of R in there and all of S in there. It doesn't matter if we dump all of R and all of S, or we dump all of S and all of R. We end up with everything from S and R, or R and S. Doesn't really matter. And the same thing here. R union with S, union with T, is the same as we do S union with T and then add R later, since it's a union operator. Okay, now with concatenation, it's also associative, meaning that if I say concatenate R with S to get that language and then concatenate that with T, that's the same as if I regroup these and say R union or concatenated with S concatenate T. Those will always be the same, have the same result. But one thing that's important to note is that concatenation is not commutative, meaning R concatenated with S is not the same as S concatenated with R. While concatenation has an associative property, it does not have a commutative property. Okay, and that brings us to the concept of identities. And an identity for an operator is a value. So an identity is not really an operator or an algebraic property. It's a certain value such that when any value is operated upon by that entity, the value itself is unchanged. So in other words, here we have X, and these are in arithmetic or algebra. So anything X plus 0 will not change X. You'll end up with X. So in other words, 0, the value 0 is the identity value for addition. The value 0 is also the identity value for subtraction. Anything minus 0 is the same thing we started with. And notice that 1 is the identity for multiplication and division. So x times 1 will always give x. X divided by 1 will always give x. So 0 is the identity for addition and subtraction. 1 is the identity for multiplication and division. Now, one related concept to that is called an annihilator. An annihilator is another value just like an identity, but what it does is rather than passing through the item, the data, untouched, it annihilates it. It gets rid of it and replaces it with a value. So notice that 0 is the value or the annihilator for multiplication. So anything times 0 is always going to result in 0. So no matter what, as long as we have some finite number here, multiplying it by 0 will always give us 0. We might say, well, what if we have an infinity there? Infinity times 0 is, well, undefined really. But in this case, 0 is the annihilator for multiplication. No matter what we're multiplying it by, it'll pass through the 0. So notice that's similar in concept to identities that we had over there, but that's how annihilators work. Now, let's look at annihilators and identities for regular expressions. So, empty set union with R, no matter what order we do it in, because we can switch these, we already had a commutative property, is always going to just be R. So in other words, empty set is the identity for union. And that makes sense. If you say, take all of what's in language R, and then add nothing to it, what do we get? Well, we still have R. We haven't added anything to it. It's the same as it was. It will always be the same no matter how many times we add no elements to it. We're always going to get the same thing. Now notice that lambda, the empty string, is the identity for concatenation. If I say empty string concatenated with some language, or if I say some language, regular expression defining a language concatenated with lambda, we're always going to get the same thing. And that makes sense. So in other words, if I have some set of strings and I add the empty string to the end of them, a string of 0 length, I just get the same set of strings that I started with. Now, moving on to annihilators, notice that empty set is the annihilator for concatenation. So if I say empty set concatenated with any language, or any language concatenated with empty set, I always get the empty set. Okay, so moving on. The distributive property essentially states that if you have one operator applied to two items that are joined together by another operator, then that can be pushed down and the first applied to each. So in other words, just like in algebra, x times, so there's the multiplication operator being applied to these two things that are joined by this other operator, we can distribute the x across each of those and get xy plus xz. So in other words, this x goes in there to the y, x goes in there to the z, so you can see it being pushed down into those parentheses and applied to the other ones first. So the multiplication now is applied first before we do the addition. So typical distribution like you're used to seeing in arithmetic. Now for regular expressions though, it's kind of the same thing. It works the same way. So in other words, that if we have concatenation being applied across these two things that are being having a union, just like we have multiplication being applied to these two things with addition, then we can distribute that in there and concatenate this, and then concatenate that, and then union those together. And that's equivalent. And also, notice there's a distinction here between left distributive and right distributive. Left means that the thing on the outside is to the left, and it goes to the left side of each of the sub-ones. If it's on the right and it distributes in, it goes to the right side of each of those. Notice that's a little bit different than algebra, because in algebra it doesn't matter if we say x times y or y times x, we get the same value. But concatenation, remember, not being commutative, that gives a different result whether we do left distribution or right distribution. But both of those hold true. We can distribute either distribute in a left distributive way or a right distributive way. Okay. Now so far most of that stuff that we've seen you've probably seen before, but there's another property here that's important to at least understand a little bit, and that's this thing called idempotent. And what idempotent, the idempotent property essentially means is if we have an operator that's used on identical values, it does not change that value at all. In other words, looking at the way this is set up here, oops, let me go back to that. I'm going to fix my bad typing. Okay, so in regular expressions, we have R union with R just gives R. So in other words, here I have R. I'm using this operator, the union operator on it, between the same thing. We'll just get R out of that. So in other words, if I have a set of strings and I union it with itself, I'm always going to get just that same set of strings. I can't get more from that. So in other words, union is what we would call idempotent. Another example of something that's idempotent is the star operator. If I take some language star and I take that whole language and I star that, it still gives me the same thing. So this would be R star star is the same as R star. And maybe I should actually put that there too. Equal R star. Okay. So notice no matter how many times I star something, it's always devolves to the same thing, star. Okay, now on to a few closure properties. And what closure properties are, remember the closures are the positive closure, meaning the plus sign, or the clean closure, which is the little star operator. And so the closure operators or closure properties are, again, here's the idempotent property we had from the previous page. Anything starred is the same as just that thing starred. Anything plus is the same as R star. We saw that from the first page. But then we also have this one. Something star is the same as that thing plus union with lambda, because that's the only difference between star and plus. Star includes lambda, plus does not. So if we union lambda in with this thing that does not include it, now it's the same as R star. Lambda star is the same as just lambda. So in other words, empty string 0 or more times is always the empty string. And that kind of goes with this bottom one, lambda is equal to lambda. And then this one's probably the second to last one there, that empty set star is equal to lambda. That's probably one that might be a little bit counterintuitive. But the reason that that is true is because anything to the 0 results, that's a string of length 0. And a string of length 0 is always going to be lambda. And then if we union that with this raised to the 1, that's just empty set. So in other words, we have lambda union with empty set, and then to the 2 is empty set concatenated with empty set, which is empty set. So we have union of lambda with empty set, with empty set, with empty set, with empty set on to infinity. So that's going to leave just behind only the lambda. All right, so those are some of the closure properties. And to summarize all of those properties that we've kind of seen so far, here's a slide that has a lot of information on it, and we'll be looking back at this. And actually, if you go to the course page, I've posted this as a handout, so you could just bring this up in its own PDF and look at it whenever you want to. But the idea here is that I've given these rule numbers. Those aren't official rule numbers that are part of like automata, like official formal languages. I just numbered them. But you'll notice we have a range of these here all the way from rule 1 through rule 15. And you'll notice that some of them, like rule 7, actually all of them, since they're equivalents, in other words, RS is equal to SR, that also means SR is equal to RS. So those equivalencies can go either way, from left to right or right to left. So a good example of that would be, for example, down here, R plus is equal to R star, which is also equal to R star R, or if I have R star R, that's the same as R plus. So I could use the either going from left to right or right to left because they're equivalent. Same thing with this distribution here. If I have RS or RT, I could factor the R out to get R concatenated with S or T. Or if I have R concatenated with a quantity S or T, that could be substituted and distributed inwards to get RS union RT. And one thing to notice is this rule 2 up here, that's the associative one. And really, since you can switch these, you could group these with the R or T or S as well. It's just not shown there because that would be a combination of 1 and 2. Okay, now what can we do with these algebraic properties of regular expressions? Well, the cool thing is that now we have this way of defining languages. And we have a way to kind of abstractly or symbolically manipulate that to say this language, or this expression that defines this language is equivalent to this other one that also defines that same language. And because we have these kind of equivalencies here with all these rules, we have ways we can manipulate one expression into another without changing the language itself. So very similar to algebra, where you have some algebraic expression, and you can manipulate it, and you can factor things, and you can regroup things, and you can shift things around in order to simplify that expression to help you solve some sort of equation for it. So we're going to do the same kind of thing now. We're going to try some reductions using those rules. So let's start out with this. So we want to know, does this expression on the left side of this equal sign, is that identical or equivalent to the one on the right? In other words, do those two things define the same language? And your first way of looking at this might be, well, I could try some strings in this and see if I can also get them with this, or I could try some strings in this and see if I also get them in that. But you might not try enough of them because this language is infinite. There could be one, just one, that's in this but not in that. And so how do we know if those things are really equivalent or not? Well, one way we could prove to ourselves that those two things are equivalent is if we can use those algebraic laws that we had over here to manipulate one side or the other or both into the same expression using one of these actual, what we call rules over here, these algebraic properties of regular expressions. So let's try that with this one here. So I'm going to start on this one on the right-hand side. So that's just it duplicated down. And I'm going to look at this right-hand side and say, does that match any of our rules? Does that thing that's highlighted in yellow there match one of the rules? In other words, something plus or lambda. Well, if we go back to those rules, do we have something plus or lambda? Yeah, we do right there. That could be replaced with just that thing star. So that's what we're going to do. We're going to replace that. We're going to use Rule 15 off that sheet. And I might encourage you at this point to go ahead and go to that handout and bring up the handout as we go through these, maybe alongside the video so you can look at that. But this is using Rule 15, which is some r plus or lambda is the same as that thing star. So this would be r in that case is what's inside of here. So we now have replaced that with that thing star. Okay, so that's using Rule 15. Well, now the left side and right side still don't match. So let's manipulate a little bit further. Well, here we have something where we have a union operator in parentheses with a concatenation after that. So with that, we could distribute that. We could use the distributive property. In this case, it's a right distributive property. So this A can be pushed down into that to give us BA union AA. And that is using Rule 8. So we use Rule 8 by distributing the concatenation on the right into that parenthesis, and we wind up with those things now distributed into there. But that still doesn't match the left side. The two expressions are still a little bit different, but now we have BA union AA. Let's focus on that. So things that are union, we can use the commutative property to switch those, and that was Rule 1. And now we have those two things matching, AA or BA star is definitely equivalent to AA or BA star. And notice that since we use an algebraic property legitimately in each of these steps, we know that our answer is right. And these two that we started with, essentially are equivalent. They define the same language. So those two original expressions are equivalent. All right, let's try one more here. All right, so this one looks maybe a little more difficult because notice we have two things that are both starred, but what's inside the star doesn't match in each of these. So you might think, well, those don't define can't define the same language because even though they're both starred, this has something different inside of there, which has this A, B, or B plus. This doesn't have any plus inside of it. And this one on this side has this lambda here, but this one doesn't have a lambda inside there except for the concatenation before the B, so these don't look like they're going to be the same. Well, let's see if we can figure out if they are or not. So again, we start with the original, and this time, notice that rather than always manipulating the right-hand side, you could do the right-hand side or the left-hand side, doesn't matter, either way. But in this case, I'm going to start on the left-hand side, and I'm going to start with that thing inside the star. Notice there's something plus or lambda, and again, by Rule 15, same way we did in the last example, we can turn that into that thing star. So there's that thing star inside of the star, But now we have something star star. So we're applying the star closure twice, and by the idempotent property of the clean closure or star closure, which was rule 10, we can replace that with just the single thing starred over here. Well, now rather than continuing to do something with this side, I'm going to jump over to the other side, and we're going to distribute this B into this. So there's an ability to use a distributive property, which is rule 8. And rule 8, the B distributes in to have AB union lambda B, and lambda B is the same as just B. So now those two things match. And so yes, those two expressions, even though they looked quite a bit different up here, they're still equivalent. They still define the same language. All right, let's do one last one. Okay, and for this last one of the things to notice on this one is we have a really complicated left-hand side of the equal sign and this right-hand side over here, which is just A star. Are those two equivalent? Well, this looks more complicated, but let's see if we can figure out if those are equivalent or not. All right, so the first thing I'm going to do is I'm going to notice we have two things grouped, and all three of them are using union. And that brings up the ability to now regroup those for that associative property. So I'm going to regroup, instead of having the A star union with A plus, I'm going to group that around A plus union with lambda. And that was rule 2. So by rule 2, we can regroup those. And now that those have been regrouped, so all we do is move the parentheses over, which we're allowed to do by rule 2. But now that we have that, we have something plus or lambda. Well, something plus or lambda is the same as star. We know that by, again, rule 15. And now we have A star or A star, that whole thing star. And now we have A star or A star by rule 1, which was essentially anything union with itself is still itself. We end up with just A star inside there. So now we have A star star and A star star using rule 10 is the idempotent property of the star closure. That's going to give me just A star. So this has now been replaced by just A star. So now we have A star or A star, which just condensing these up so we can fit it all on one page. So I just slid everything up there. So now by rule 9, and actually this is probably supposed to be rule 9 up here as well. But that now, anything union with itself is itself. So A star is now equal to A star. And we have, yes, those two expressions had to have been equivalent because we can manipulate them by those algebraic properties in order to get them to match. Now, one quick question. If you can't manipulate one into another, does that prove that the two languages are not equivalent? So let me give you a second to ponder that. So let's say you have two expressions and you spend some time manipulating them and you don't get something that matches. Does that mean that the two equations, or the two expressions, the regular expressions, are not equivalent to one another? And the short answer to that is not necessarily. It could mean you're just bad at manipulating them. It could have meant you made a wrong turn somewhere, or it could mean that the language that you're trying to manipulate is, the expression you're trying to manipulate is just complicated and it's not an easy thing to manipulate it. But it doesn't necessarily mean that the two languages are not equivalent. Now, if you can manipulate one and have it be like A plus on one side and A star on the other, and you've done legitimate manipulations, then yes, that proves they're not equivalent. But just because you can't do it doesn't mean that it can't be done, and it doesn't mean that those two are languages. So in other words, it's difficult to prove that the two languages are not equivalent, but you can prove that they are equivalent. So if you can manipulate one into another, does that prove that the two languages are equivalent? Yes, absolutely. As long as you applied those algebraic properties in a appropriate way. Okay, so that's all for today. I would suggest working on the lab. I would also suggest doing the assignment, or working on the lab. Also, or I guess I should say, I would also suggest being ready for a quiz and taking a careful look at those algebraic laws of regular expressions, because that will be something that will be on a quiz coming up. So that's it for today. There's only really a half hour there. I want to give you some time to work on the lab. If you have questions on any of those, let me know. Make sure to submit that by the due date. And next class, we're going to dig into some of these algebraic properties of regular expression a little more, and we're going to use that as a starting point for proof, which we are going to do a little bit of proofs in this class. We're going to do some kind of theoretical proof things in here. But we're not going to spend a whole lot of time focusing on just that in this class, but it is going to be something that we're going to spend some time on. So we're going to start with essentially stuff like we did back here, that this is essentially a proof that that is the same expression as that. It's a direct proof method. We're going to talk about that. We're going to talk about some other proof methods coming up. Other than that, that's it for today. Everybody stay safe. Get ready, be ready for quiz, study those algebraic properties of regular expressions, and maybe go back and look at those manipulations that we did to make sure that you understand the way that those are applied. All right.